Hi everyone, welcome back. Welcome to part 2 of Factorial Analysis of Variance in SPSS. In part 1, we talked a little bit about analysis of variance. We went through the example where we were comparing reading comprehension scores for adults who either had practiced or had not, and who were tested in a room where there was either no background noise, some background noise, or a high level of background noise. We checked our assumptions and we determined that all 6 of our cells, all 6 of our samples were approximately or sufficiently normally distributed. And then we set up the analysis of variance. And that's where we're up to now. So we've just generated all of the output. And let's take a look at it. What I'd like you to do is get your output and let's have a look. So I'm going to scroll through this quickly, and then we're going to look in some more detail at individual tables. So we've got a between subjects factors table that tells us how many observations there were at each level of each independent variable. Remember, we've got 30 participants total. Half of them had practice, so 15 of them had some practice, 15 of them had no practice, and then there were a total of 10 participants who took the reading comprehension test with no background noise, 10 with some background noise, and 10 with high background noise. And of course, those were split 5 who had no practice and 5 who had some practice. The second table is descriptive statistics. Then we've got Levene's equality of error variances. So this is a kind of general test of homogeneity of variance. There's our between subjects effects. So this is kind of like our ANOVA source table. You'll notice it's a lot longer than the ANOVA source tables from tutorial number 6, the Pink Book chapter 7. We've got 5 different groups of estimated marginal means with some post hoc tests, some simple contrasts, and other things that we are going to look at in a lot of detail. And then I asked for 2 profile plots, one showing levels of background noise on the x-axis and practice as the different lines, and then one with practice on the x-axis and levels of background noise as the different data paths. So let's start with the descriptive statistics table. And let's compare means for practice versus no practice. And when I say practice versus no practice, I mean I don't care whether participants had high, low, or no background noise. If they had no practice, what's the mean score? Or if they did practice, what's the mean score? And that's what we get from these total lines. Right? So all 15 participants who took the test with no practice got a mean reading comprehension score of 12.6 with this standard deviation, and again, here's the sample size. So we can see that participants who did have 10 minutes to practice did seem to get higher reading comprehension scores, right? 15, closer to 16 than to 15, than the participants who did not practice. So they got about 3 points higher. And then if we compare noise levels, so ignoring whether they practiced or not, was there a difference in reading comprehension scores for no noise, low noise, or high noise? There we want to look at the total column down here at each of these 3 values. And it does look like comprehension scores were highest for the no noise group and lowest for the high noise group, which is what you might expect. Now, whether that's a statistically significant effect, we can't tell from these individual group means. Finally, let's compare individual cell means. So if you think back to that table before, we had 6 cells organized in a 3x2 grid. Right? So based on no noise, low noise, or high noise as a function of no practice or some practice. So these 6 values in these 2 pink boxes reflect what I'm calling the individual cell means. And it can be difficult to interpret these individual cell means, but what you might notice is that at each level of noise, the practice group has a higher score than the no practice group. So that's one takeaway. All right, I've ignored the standard deviations for the time being and just reorganized all of those means. So these 6 individual means that I called individual cell means, I've put into the individual cells of my table. Now, this number 12.6 is it happens to be the mean of these 3 means because my sample sizes are equal. But what's important is that it's the mean of all scores, the mean reading comprehension score for all participants who had no practice. That 12.6, so that's where I got that. And similarly the 15.7. So these are marginal means. They're referred to as marginal means because they are the means that go in the margins of your table of cell means, right? So here are the cell means, the means of those means, or the means of all participants that contributed to those means are your marginal means. So here's the marginal mean for the no practice group, marginal mean for practice. This is the marginal mean for no noise, so that's all 10 participants who took the test with no noise. 14.7 is the marginal mean for the low level of the noise factor, and then 11.8 is the marginal mean for the high level of the noise factor. All right, I'll give you one guess as to what this Granddaddy bright pink number is. Have you got it? That's the grand mean, right? It's the mean of these 2 marginal means. It's also the mean of these 3 marginal means. It's the mean of these 6 cell means, and it's the mean of all individual scores from all 6 cells. So this is the mean of all 30 individual observations, ignoring what group they come from. So that's the grand mean. When we have unequal sample sizes, this is not going to necessarily match up with the means of individual cell means or individual marginal means, but it's always going to be the mean of all observations in your data set. All right, moving on to the Levene's table. So we've got a Levene's test for equality of error variances, which is on, if you notice, we've got 5 degrees of freedom, which tells us that it's just on those 6 individual cell means. But we've got 5 and 24 error degrees of freedom with a p-value of, well, with an F ratio of 1.1, just a little bit bigger than 1, and a p-value of 0.37. So what that tells us is that the assumption of homogeneity of variance is not violated. And we can write it like this, with the F of 5 and 24 degrees of freedom equal to 1.127 or 1.13. All right, so that tells us that it's reasonable to look at the next table down, the tests of between subjects effects, because this table assumes homogeneity of variance. Now, SPSS is not equipped to report robust tests, so the Brown-Forsyth or Welch's tests for factorial analysis of variance. I really don't know why. It's not because such robust tests don't exist or because they're too mathematically complicated for SPSS to handle. I really don't know why, but it doesn't. So what the Pink Book recommends that you do essentially is try not to violate the assumption of homogeneity of variance, which, good advice. And Fields gives 2 other alternative suggestions. One is that you use bootstrapping. The other is that you try a different statistical package. For example, R, which is an open source package, is much better equipped to report robust tests of factorial analysis of variance in the event that you have violations of homogeneity of variance. However, for Psych 202, let's keep things simple. Just understand that if you did have a violation of homogeneity of variance, you would want to report something like a Welch's F or a Brown-Forsyth F instead Luckily, we don't have that, so we're not going to worry about it. So we can look at this test of between subjects effects table. You'll notice that it reminds us what our dependent variable is, reading comprehension level. And then we've got 1, 2, 3, 4, 7 columns. The source, this is our ANOVA source table, and you'll notice it's got a lot more lines than the ANOVA source table when we did a one-way analysis of variance. But just like one-way analysis of variance, we've got sums of squares, degrees of freedom, mean square, F, and then a p-value. And then as a little bonus, we've got an effect size, partial eta squared, so we don't have to calculate eta squared ourselves. You can read in field, or hopefully we'll have covered in the lecture, what it means by partial eta squared. But in effect, we are talking about the same effect size, same eta squared effect size that we talked about in topic 7. All right, so the first row of this test of between subjects effects table is the corrected model, and you'll notice that it's got 5 degrees of freedom, it's got an F of 14, so it's statistically significant, it's got relatively pretty high, impressive partial eta squared. We're not actually interested in that in this case. What that first row of that particular table tells us is that the cell means are better predictors of the individual scores than the grand mean. So all that says is that all scores are not equal. So no big surprise. And it doesn't actually help us answer our research questions about the separate and combined effects of practice and background noise on reading comprehension. Similarly, the second line of this table is not something that we're going to report. So that intercept variable, what that just tells us is that the grand mean is significantly different from 0. So the fact that the intercept row gives us a gigantic F ratio and a small p-value that tells us that this is significant and a very, very large partial eta squared. All that says is that the grand mean is not 0. So again, we already knew that. That doesn't help us answer our research questions. The first row that does help us answer our research questions is that third row. You'll notice the source there is practice. So this is about the main effect of practice. If we look at that, we've got 1 numerator degree of freedom. If you recall, the practice variable was either they practiced or they didn't. So there were 2 levels of that independent variable, which means we're comparing practice versus no practice. So we're comparing effectively 2 sets of groups, which means we have 1 degree of freedom. F ratio is 27 over 27, so our p-value is less than 0.001, and our partial eta squared is about 0.54. So that's a significant main effect. Oh, and we get the degrees of freedom, their denominator degrees of freedom from this error row in all cases for factorial analysis of variance. So there is a main effect of practice with an F ratio with 1 and 24 degrees of freedom of 27.84, a p-value less than 0.001, and a partial eta squared of 0.54. Next, there's also a main effect of noise. Now you might remember from when we looked at this descriptive statistics table that reading comprehension scores were highest when there was no noise and lowest when there was high noise. So we can probably conclude that noise has a negative impact on reading comprehension score, but we'll need to do some follow-up tests to specify which levels of this independent variable are significantly different from each other. We can still report there's a main effect of noise. F this time has 2 and 24 degrees of freedom. Remember, we've got 3 levels of this independent variable, so we've got 2 degrees of freedom, 2 numerator degrees of freedom, and the same number of error degrees of freedom as ever. Now our F ratio is 17.54. and our effect size is 0.59. So you'll notice that even though the F ratio is a little bit lower than it was for the practice main effect, the effect size is a little bit higher. You can have a smaller F ratio and a bigger effect size. All right, and finally, there is a practice by noise interaction. So if you think about those 6 cell means, we pointed out that comprehension scores were higher at all levels of background noise with practice than without practice. So we might infer that noise had a larger negative impact on readers who did not practice than on those who did practice. But again, just like with the effect of noise, we need to do some follow-up tests to confirm. So here's the first of 5 estimated marginal means sets of results. And you'll notice that each of these comes with 3 different tables. One that describes the estimates, which gives you your confidence intervals at each level of the independent variable. So here's the marginal mean for no practice and the marginal mean for practice with 95% confidence intervals for each of them. The pairwise comparisons reported as Fisher's least significant difference, and then the univariate test looking at, is this a significant contrast? So based on the fact that there's a significant main effect, there's only 2 levels to this independent variable, we could report that readers who practiced first had significantly higher scores than those who did not, and then report the main effect F ratio, p-value, partial eta squared, etc. However, the conventional practice is to interpret statistically significant interactions first. So we would only examine these main effect results if the interaction was not statistically significant or if there was still some ambiguity about what the effects were after we interpreted the interaction. So we're going to skip over this for now. Similarly, we're going to skip over the main effect of level of background noise. Here's the third set of estimated marginal means output. Now this is the one where if you didn't edit your syntax with me at the end of part 1 of this tutorial, then you probably don't have these variables. So you don't need to worry about it if they're not there in your output, but do follow along now so that you know how to interpret these results. Now again, we've got estimates of the mean with the standard error and 95% confidence intervals. In this case, we're looking at those confidence intervals for individual group means, so individual cell means. And you've probably noticed that the standard error is the same for each of those 6 cell means. That's not unusual, don't be surprised by that. That's because we're assuming equal variances. So what we've done is taken a pooled estimate of all of the 6 different standard deviations from each of our samples, and we've pooled them to get one estimate of population within group population variance. So that's why that standard error term is the same for, for all groups. Now that second table down is the pairwise comparisons table. Now if you look at that, you might conclude that the reading comprehension scores were lower for no practice than they were for practice at the no noise level of background noise. So a significant difference between no practice and practice. And also at low noise, there's a significant difference between no practice and practice. Although there's no significant difference at the high level of background noise. However, also notice that what's been reported here is not Tukey's HSD, but Fisher's least significant difference. And Fisher's least significant difference, as it says at the bottom of the table, is equivalent to no adjustment. So what we have here is an inflated type 1 error rate. So we can deal with that by just running Tukey honestly significant difference post hoc tests. We could go back and do those, or we can do a Bonferroni adjustment. However, rather than report the pairwise comparisons, what we want to do is look at the univariate test. So this is the simple effects that we were talking about. A simple effect is looking at breaking down a factorial analysis of variance into multiple one-way analyses of variance. So in this case, what we're doing is we're testing whether the effect of practice is statistically significant at each individual level of background noise. So you may notice in this univariate tests table that it looks like an ANOVA source table, very much like before. We've got a sum of squares column, degrees of freedom column, mean squared, an F, a significance level, and a partial eta squared. However, unlike the previous ANOVA source table that we were looking at that had a lot of rows, this one has 6 rows and 3 of them are exactly the same. So we've got a contrast and then an error term, and a contrast and an error term, and a contrast and an error term. And the error term in all 3 cases is different. The contrast term happens to be equal in 2 out of 3 cases. That is not something to be expected, but the fact that the error term is identical for all 3, right? We got sums of squares of 60.8, 24 degrees of freedom, and 2.533 as the mean squared error. So that MS error estimate is the same for all 3. Going back to this previous test of between subjects effects table, notice that that's the error term we got from our omnibus analysis of variance. So what we're doing here is separate one-way between groups analyses of variance at each level of background noise, but instead of using the error term, so the MS within or MS error from each individual analysis of variance, we're just replacing that with the omnibus error term. We still have the same problem, which is that we're doing multiple comparisons and we haven't done anything to adjust for the type 1 error rate. So what the pink book suggests you do is you do a Bonferroni correction, and that's something that you can do kind of in your head. You don't need to do anything different in SPSS. And the Bonferroni correction that we do in a simple effects analysis is that we modify the alpha level by the number of levels of the other independent variable. So in this case, the other independent variable is the one that we're doing separate analyses on. So background noise is the other independent variable in this case. So we want to divide our alpha by 3. If you divide 0.05 by 3, you get 0.17. And actually you get the same result that you would have if you'd used an alpha of 0.05, but that's as it happens. So the significance, the p-values for the no noise comparison and the low noise comparison are less than 0.001, which is definitely less than 0.017. And the p-value for the high noise comparison contrast is greater than 0.017. It's actually greater than 0.05. So what this tells us is that comprehension scores were lower for no practice than for practice when there was no background noise and when there was low levels of background noise, but not when there were high levels of background noise. Okay, so we've looked at the simple effect of practice at each level of background noise. Now we need to look at the simple effect of level of background noise at each level of practice. So again, we can kind of skip over in the interest of time. This estimates table is exactly the same as the estimates table for the previous example, but do notice that there are more pairwise comparisons for this simple effect than for the previous simple effect, because this time we're looking at 3 groups at each of 2 levels. So we've got 3 pairwise comparisons times 2 levels, instead of looking at 2 groups at each of 3 levels. So when you're looking at 2 groups at each of 3 levels, that's 1 pairwise comparison at each of 3 levels is 3 comparisons, whereas in this case, we're looking at 3 groups So 3 comparisons per level times 2 levels is 6 comparisons. So we've actually got a larger pairwise comparison table. We've still got the same issue that we haven't adjusted for the inflated type 1 error rate, and we've also still got the issue that what we're particularly interested in is the simple effects, this univariate tests table. We have to do the same thing. We have to, in our heads, adjust the alpha, so our criterion for statistical significance. This time, in the simple effects analysis for level of background noise, we're again going to modify our alpha level by the number of levels of the other independent variable. In this case, the other independent variable is practice, so it has 2 levels. So we want to divide our alpha of 0.05 by 2. So for each of these comparisons, we judge them to be statistically significant if they are less than 0.025 instead of less than 0.05. And what we get out of that is the same thing that we would have got if we had stuck with an alpha of 0.05, but that's all right. The effect of level of background noise is not statistically significant for the participants who did not practice, but it is statistically significant for those participants who did practice. In other words, there was an effect of background noise, but only for those groups who practiced first. All right, the last thing we're going to do with these outputs is look at the profile plots. And the pink book only asks you to look at one of these, but I'm going to look at both because I get something meaningful from each of them. Now, I wouldn't include both of them in a results section because they're showing me redundant information. And of course, I wouldn't include them in a results section as they are anyway. But when I look at this profile plot that plots level of background noise on the x-axis and practice or no practice as separate lines, what I see is that comprehension scores were lower for no practice than they were for practice, and that difference was there basically at the no noise and low noise levels, and seems to be not so much there at the high noise level. So I can intuit that there's a main effect of practice because the marginal mean, so the mean of the 3 green data points is pretty different than the mean of the 3 blue data points. I might conclude that there's a main effect of level of background noise because if I think about the mean of these 2 points, so the 2 means for no noise versus the 2 means for low noise versus the 2 means for high noise, if I were to draw an imaginary line halfway between these two, it would not be a flat line, right? There would be a negative slope. And I can infer that there's a potential for interaction. I can infer that there's an interaction because these 2 lines are not parallel. Right? We can also look at the same data graphed a different way with practice on the x-axis and different lines for different levels of background noise. And what this profile plot tells me is that there was an effect of background noise, but pretty much only for the groups who practiced first. So if you look at high noise versus low or no noise, there's a big difference for the practice groups, but it's much smaller for the no practice groups. Okay, so to wrap up, if you want details on calculating an unbiased estimate of effect size, that is omega squared, you can look at pages 102 to 104 of the Pink Book. Allen, Bennett, and Heritage state that the use of partial eta squared, the effect size that's provided by SPSS, is not generally recommended. I have to admit, whether it's recommended or not, it is the effect size that I see reported the most frequently. That doesn't mean that they are wrong about omega squared being a preferred effect size over eta squared, but for our money, given the time that we have available to us, I'm not that interested in going over those calculations, but they're not difficult to do if you are that way inclined. The other thing is that I encourage you to see pages 104 to 105 of the Pink Book for details on how you might write up these results in APA style. However, if you're going to do that, notice that they included figure 1. If you're going to do something like that, do not simply cut and paste a graph from SPSS into a report of results. You need to tidy it up first, and by that I mean get rid of all of the extra wording around sort of titles and that are not needed. Make the legend look a little bit nicer. In particular, fix that y-axis scale. My goodness, it really does exaggerate the magnitude of the effect when your y-axis scale goes from 11 to 18. And similarly, if you include error bars, you'll be showing a much more representative plot. All right, if you haven't done so, now's a good time to save your output file again. I hope all of that makes sense, and I will see you in part 3.